Good afternoon, everyone. Welcome to another session of the Network Seminar series hosted by the Center for Network Intelligence at the EC and RBCC here, IIT. Today's topic by Dr. Pannag R Sanketi, and he will be speaking on an overview of robotics research at Google Deepmind. Dr. Sanketi is currently a tech lead manager in the robotics team at Google Deepmind in Mountain View, California. He leads various projects on robot learning, including X-embodied fountain models, agile robots, such as table tennis and catching, infrastructure for connecting multiple robots. Before joining the robotics team, he worked as a tech lead in Android for many years, where he developed AI features for Android apps such as Camera, Photos, and Pixel Watch, founded on device ML projects. Prior to Google, he worked at a computer vision-based startup called PixBlitz, and then at Smith-Kettlewell Eye Research Institute in San Francisco as a research associate, developing computer vision-based cell phone algorithms to help visually impaired people. He did his undergrad from IIT-Madras in mechanical engineering. He obtained his MS and PhD from University of California, Berkeley in 2005 and 2009 respectively in control systems and optical control. His research interests lie at the intersection of robotics, optical control, and machine learning. We would like to request our online audience to please keep your microphones on silent during the duration of the talk, except when asking questions. Over to you.
Oh, thank you so much for the kind introduction. Can everyone hear me? So awesome. Thank you so much for the kind introduction. So, and it's my pleasure to present an overview of research at Google. Now we are actually Google Deepmind. So the merger happened recently. The slide still follows like robotics at Google, but now Google Robotics is the same as Robotics Deepmind. Yeah, let's get started. So here's what we're going to kind of cover for today. Basically, I'll kind of give like an introduction to the robotics team at Google Deepmind. Then I'll give like a drive-by overview of a few sample projects at Google Robotics. Basically covering manipulation, navigation, locomotion, agility, and also cover like language as a bridge between AI and robotics, which has been like a big search for us recently. And then towards the end, I'll touch on like the opportunities for faculty and students to get involved. The pace of the kind of talk is going to be pretty brisk. So basically, I'll go through like a quick pace. It is more of like what do we do kind of talk, and I'll touch upon the key kind of highlights of each project. But we won't be going into like the how in detail, but the like links and the slides will be shared later, and we can kind of dive deep into like how each of those things are done later. But if any acronyms I use, I kind of assume certain kind of understanding of machine learning things. So if you see any acronyms, so if you see any kind of technical terms that you don't understand, feel free to interrupt me. I want to kind of keep it informal, so please don't hesitate to kind of ask us. Also, another important thing is that I'm doing the work of many people, including like many external collaborators that we do. It is not all my work, and also separate to all those people and my overall team of them. All right, so who are we? We are basically a team of researchers, engineers, and designers. At the base of it, we are a research team. So we don't have any product. Basically, unlike other research teams at Google who funnel their research output into like Gmail, search, YouTube, whatnot, we don't have that. But we are just research team, but we do have engineers who come from like product background, designers who come from like UI design background, and of course researchers. This is a photo from a few years old. We don't have a team photo like this, so heads are rolled, but still the speed stays the same. Our mission is to kind of make robots useful in the real world through machine learning. Basically, why that is the case? Because we want to rely on our strengths. As you might guess it, like Google's strength is machine learning, and there are lots of like very well established robotics kind of labs around the world who are doing fantastic research in robotics. So we wanted to kind of bring our strengths to the field, and hence we want to kind of make use of machine learning and then use that to make robots useful in the real world. And the North Star that we're aiming for, like when I think of it, we don't have a product like say, but as a research goal, what we're aiming for is to develop a robot generalist that can help humans in social environment. For example, in elderly care, or in kind of your home environment, or in restaurants, hospitals, wherever there's like a social interaction between humans and robots. Cool. So the question kind of becomes, okay, how are we grounding our research? Because it seems like very blue sky kind of things, right? How do we ground our research? The way we do it is like we define certain benchmarks. So we like have certain tasks that were chosen, which kind of span the overall set of tasks in robotics, and we use that kind of measure our progress. A few samples are shown here, like 10 to 12, we are shown like 6 here. So on the top left, we can see one of the tasks that we're trying to solve is for inspection. So here you see like mobile manipulator being given inspection of like going and finding something and then reporting back. In the middle top, you see what we call as feature folding. So this is like getting into soft coding manipulation task. It's very different from like hardware dynamics. On the top right, you see a ping pong or table tennis that is called. This is in the realm of agility. So here we have robots move very fast. On the down left, you see like motion and obstacle course. We have different kinds of obstacle course. One kind of them is shown here. Then we have something called instruction following, in which like we have things such as office kitchen, where the user can give input in free form text, and the robot has to try and follow, carry out those instructions. And similarly, there's like a tabletop environment where it's like a natural interaction in real time using language. So here's like a few sample projects. And now what I'll do is I'll kind of take you through a few chosen projects covering these tasks and give you an idea of what we are doing there with like some key points. Cool. Manipulation. But if you folks join late, this kind of connective. So this talk will be just kind of like a drive-by overview of what we do. There's like details on the slides for you to kind of follow later. But if some things are not clear, feel free to kind of raise your hand at the back. So the first kind of domain that I cover is manipulation. So goal in manipulation is to build a robotics foundation model, which can basically be robot agnostic, environment agnostic, and task agnostic, right? So and to do this, basically we would like to scale up the robot learning, basically scale up the model size, scale up the compute, and scale up the data that we put into it. Why one might ask me, why do you want to do this, right? Just because it's the language models, should we do it in robotics also? And the answer that we're thinking is that not only does it kind of solve complex tasks, of course, but we are thinking that we as Google are in a fortunate position that we can invest a lot of resources in collecting data, in collecting basically labeling the data and creating a data set which is kind of available for free for text, like in internet scale data available for text, but robotics is not. So we hope to kind of open source this data set so that smaller labs then can take advantage of that and then only fine tune those models rather than kind of recreating the whole function. So the early days of our manipulation project, like back in 2016, 2017, started with like what we call a farm. So here we said, okay, how does machine learning work at Google? Basically, we kind of take we scale the infrastructure, we give more data, and we kind of train large models. So with an aim to do that, we set up something called arm farm. So here we set up like something around like 14 robot arms that are basically collecting data for like 3 months. And over 3 months, we basically kind of collected 800,000 graph attempts, and all were kind of basically network arms. So basically, this kind of gave us like the first data set to take a crack at this robot learning problem. And the first kind of project that we work on is what we call as 2D op. Basically, this was like a deep reinforcement learning for vision-based robotic manipulation. And here the idea was that we have something called 2D op, like a dynamic programming-based approaches. Apologies if I'm going acronyms out there, but basically this kind of reinforcement learning assumes like a value function and you try to learn the value function, and based on that your policy which grasp the object. And we can see that basically it shows 96% grasp of self on unseen objects. And basically this was like really something that we had not seen before, so it's like a huge success for us. Of course, it only worked on tabletop environments as opposed to being in the more realistic environment. But nevertheless, this was a great first milestone. Further on, we said, okay, now we kind of tried to make it work. How about we kind of take the lab setting and try to make it a more realistic setting? So what we did was we further scaled up the RL to do some realistic tasks. Like in offices, we have these trash cans, and we set out to kind of do trash sorting so that like, the recyclable paper goes to paper bin, the compost kind of goes into compost bin, and so on and so forth. So in this project, basically we took the previous approach and we had to kind of do like a bunch of engineering work on top of that to kind of scale this up to something like a trash bin. So you can see in this case, it starts out with like a simulated kind of policy. We have a simulation for the robot. It goes and kind of learns a policy in that. Once it does some decent thing, we deploy in the real world. In the real world, in the beginning, we do a lot of mistakes, but those cannot get detected and labeled. And based on that, basically, you cannot keep putting that data back into what we call as replay buffer, and it kind of continues learning that, and that's kind of the realm of reinforcement learning. The main kind of key point here is that you need some initial policy to give us some good data. If you kind of throw like a very nice robot out there, it will take very so you kind of get to follow a lot of hurdles of like how to bootstrap, how to combine data, how to weigh the different data sets. So those are some of the key obstacles we have to kind of overcome. But once you have that kind of engineering point, then these are yes.
So the mistakes, what kind of mistakes were there? Were there mistakes in picking it up or mistakes in labeling and putting it in the right place? And
So,
how did you label the mistake? Manually, like look at the video and manually annotate the
yeah, so basically, the question was like how we can label it. So this one is reinforcement learning. So basically, the structure detector kind of label the things that okay, this was done correctly or not correctly, and we use something like for crowd compute to kind of label those episodes, and that gives us the actual label.
So some humans are
Exactly. Exactly.
Okay, so then those episodes have a reward. I guess the
Correct.
give a reward and then
Correct.
put it back.
Yes, in parallel, also like an effort to do success detection kind of model. But in the beginning, definitely all the labels for success or not came from actually manually labeling kind of thing. And then we're trying to learn a robot kind of a model to do the success detection automatically on top of that. I don't recall whether in this particular paper we use that success detection model or not, because it, at least at that time, we were kind of at the level of manually.
Are there any issues? Like, did you also does it pick up paper like you just took them?
No, it doesn't because that's yes.
The question.
Oh yeah, yes.
So in the initial phase, how exploration. So
Then come again?
in the initial phase of R20, exploration.
Yes, yes.
So to assist the exploration part, you are doing this kind of to support the to assist the exploration part, you are doing labeling.
No, to kind of support the exploration, what we do is basically kind of first training simulation. So in simulation, like you can consider this like free, right? Because you can kind of collect a lot of workers and do it. And once you have the initial kind of policy, then it kind of does give you some decent episodes. So the main kind of key point to hit there is that we need some successful episodes for it to kind of do better. And exploration is built into this future method. So basically what happens is whenever you're taking actions to collect data, there is always like a what we call it like epsilon action where with some probability you take a random action and with the 1 minus epsilon probability you take the max kind of action. So that's what exploration follows. Yeah. Question?
You talk more about success detection.
Yeah. So success detection is like if you see the video, right? So it's basically kind of sorting like here there's like 3 bins, right? Like blue, green, and red bins, and certain things have to go into certain objects for it to be successful, right? So in the beginning, once we kind of collect some episodes, we will kind of label them through manually. We'll send these videos to the one, and then the basically the episode is successful if the process started correctly or not, and that's what gets fed into our.
But you said it is automatic.
Correct. We try to train that. I don't think the model kind of matches the human levels correctly. So the idea is that if we give you the whole episode, can we kind of train a vision model to kind of say that whether it's kind of detected, whether it's successful or not. Maybe take one more question.
Can you give an insights about the space tool and how you come up with the reward function and also the sim to real transfer?
Yeah. Yeah. So great question. So basically, the various kind of things go on the input side. The input is just an image. So all this kind of algorithm, this one and previous slide show the input to the algorithm is just an RGB image, and the output is typically like a 7 degree of freedom or 9 degree of freedom output, which is like the end effector post and the ripple open close, and if it's a mobile manipulator, it has 3 degree of freedom for the base. So basically pixel to controls. In terms of sim to real, basically what happens is we try to kind of train a GAN. So folks are familiar with like generative adversarial networks. what we do is we give them kind of paired images of sim and real objects. And basically, we try to make sure that when the policy trains on the simulated network, it tries to kind of almost make it look like it's kind of the real image. And then kind of try to kind of do that. So there's a separate paper we call it cycle GAN or CG GAN, and that's kind of not into the things, but that's how we try to reduce the simulated to real gap. But that's not to say that in real gap doesn't exist. So we definitely need to kind of collect. So like this kind of collection took like 23 months or so to kind of get this level of performance. So definitely the gap exists. You just need to kind of keep collecting, get some successful rewards, and do that. On the kind of rewards thing, here I think the sparse rewards. I can go back and double check, but on the rewards, here just like successful, not successful. So there weren't any kind of continuous rewards like you might have in other programs. Cool. Let's move on. So we kind of actually put this in one of our kind of Google buildings, and we actually saw that the dimension reduction like by 15% in that. So more details are available in the paper. In the interest of time, I'm just gonna keep going. Cool. So basically, as we were developing these things, we started realizing that RL is pretty painful. So yes, it kind of works, but if you kind of do RL from scratch, you are kind of looking at months and months of kind of things. Right? So that's where thankfully in parallel we also use teleoperation. It's not a very kind of intuitive interface, but it's one way of collecting data where the teleoperator basically kind of does something and the robot arm covers that, and that gives us kind of like some ground truth data to train the things, right? So now the earliest project that used this kind of things was what we call as multitask PC or BCG, D for zero shot learning. So here the idea was pretty simple. We collected like a few hundred hours of data from teleoperators. So basically, we were given like different kind of tasks, and all of them were given like a language condition. Like so, they were a task like, hey, put the banana in the red cup, put the spoon next to the cup, right? And then they actually kind of teleoperated the robot. Here, the input space was again RGB image and the freeform text, and the output was like a 7 degrees of freedom. Ripper post plus like ripper, the animated post plus ripper open close, and we basically trained like a supervised learning model. And this was one of our first forays that kind of told us that wait a second, maybe we are kind of going too far in the RL realm. Maybe we should take step back and get supervised learning. And this kind of showed around 50% success on unseen task instructions because we are relying on the language model, but we did not at this point what is going to become like a mainstream thing. So later in the talk, I'll show you more language condition policies on manipulation. But this was like our first foray into language condition model. Cool. Yes, I'll talk a little bit about navigation, right? So we'll come back to the manipulation, like I said. So in navigation, the idea is to basically try and do safe and autonomous navigation in human-centered environments. And here we are differentiating navigation from linear locomotion. So in this project, basically we tried like NTC and all to kind of put all the was in NTC. And here typically the idea is that the input is again an image of the things, and the output is your baseline. So that's the kind of thing here. And as we're kind of doing NTC, we started noticing some issues with that. There are quite a few methods, but the one that I want to kind of highlight is something called performance NTC. So what was happening with NTC was that, and see in the top kind of picture, NTC tried to optimize very well for the kind of the best part, and it's not necessarily socially appropriate. For example, like the human is coming, it doesn't understand, or it's very hard to kind of put that in the cost function, such that you kind of put all the nuances. Okay, if the human is hesitating, then you can go use space or so on. So what we wanted to do was like, okay, can we actually make it learnable cost function so that now we can actually try and demonstrate to the robot how to do good socially kind of things, and then learn it end to end. That was the genesis of what we call performance NTC. It has basically two parts. One is the learnable cost function part, and the second is the performance part, right? So let me extend that. So here, basically, the idea of the learnable NTC part is that we take the standard linear cost, we put in like some standard kind of cost functions there, which we know how to put it, right? But then there is like a learned part of the cost function based on some embedding. I'll come to that. But the idea here is that you want to learn some cost function that comes from demonstrations that encodes like the human knowledge of how to behave in a social setting. So we kind of collected a lot of data where the person was delivering the robot, and if we kind of had it intersect with like bunch of humans, sometimes the human gave way, sometimes they gave way, and so on and so forth. And that becomes kind of part of the imitation loss. And that kind of is basically back propagated throughout these things, and that's how we learn the cost function. Now the performance part is coming from like how we formulate the cost function. The input to the overall kind of thing is the overall occupancy rate of the room, and this basically goes to a transformer network. But people who are familiar with transformer networks, it's kind of very inefficient. It's like quadratic in the amount of tokens length we have. So to reduce that to linear time, we came up with this thing called performer that basically does like path matrix factorization to kind of take this quadratic cost function and convert it to like linear cost function. And that's how the performer and the runnable MPC comes together and learns anyway. And as a result, you can see that it works pretty much better than just the MPC. So you see three methods there. One is called like regular MPC, where there's no learnable cost function, and there's something called explicit policy. Explicit policy is just kind of doing peer cloning on the robot without actually kind of having this component. So be kind of like constant maneuvering, be it learning to anticipate pedestrians, or kind of like you can see the number of pedestrians is coming. It's basically making sure that it's not kind of getting too close, so it's kind of comfortable for the human. So in all these kind of things, like even the blind corner, we saw that this performance was much better than regular PC or explicit here. Cool. A quick check. How is the pace? Am I going too fast? Slow? Okay, so far so good. Okay, cool. Cool. We will share the slides later, so all the links are there. You can definitely follow up. But my aim is to give you like the overall breadth of what is going on, and so that you have like a good map of the overall thing, and then you can kind of go and kind of poke at things. So the next kind of domain that I want to touch upon is locomotion. So here the idea is to kind of enable naked locomotion to go anywhere. So as you might have guessed, if the robot has wheels and just go down the stairs, it's going to fall, right? So we are also investing a lot of research effort into wheel-naked locomotion. So we are basically kind of investing in different methods. So the first kind of level method we're doing is again RL. You will see like this trend, you know, like most of our domains have RL and BC components because our lab has both RL kind of expertise, and BC means we have cloning, but also called as imitation learning, which is to supervise learning. So in beginning, basically kind of started with developing the reinforcement learning algorithms, and out of our lab came this method called SAC, which stands for stop actor critic. And this is one of like the typically state-of-the-art methods in reinforcement learning for robotics these days. And basically, this kind of gave us this performance. It wasn't necessarily like as good as we would kind of like in all the kind of cases, but definitely it's like a great initial starting point where we're getting like good efficient and safe locomotion controllers. And we also could add safety constraints to the SAC. And this basically was our initial foray into locomotion. We also basically did learning in the wild, where basically what's happening is once it's trained in the lab, it's kind of continues to train in the real world out there, and basically is able to walk in the wild there. And we also kind of create some reset policies where the idea is that if it fails, we have a recovery policy that kind of recovers the robot and goes back, right? So this was kind of our initial foray into kind of low-level controllers for RL. By the way, in all of this, there is some state estimation algorithm going on, which kind of give it like some idea of where it is in the world. So this is not based on vision input; it's based on some state estimation. At the same time, we are like, okay, a lot of traditional kind of robotics lab use traditional kind of optimal control based algorithms like simple MPC to try and do that. So we basically wanted to invest in that also. So the two kind of papers that you see are like a combination of traditional controls and new controllers. So in this kind of work, what we did was we basically had like a high-level controller trained in RL, which was trying to kind of set the gate parameters, and then the low-level controller, which is based on MPC, which says, okay, if you want the gate parameters, the gate parameters can be something like where to put the foot, how kind of frequently to move, and that then is passed on to the low-level MPC controller to actually kind of figure out like, okay, where to actually place the foot or how much torque to give at each joint. So this was kind of like a hybrid of deep reinforcement learning algorithms and traditional kind of MPC algorithms to kind of give us better case than. Then we said, okay, we also need to kind of now start doing for both unstructured real world environments, right? Because so far it's like when somebody is giving us a say estimate, and that doesn't scale very well as you start going outside. So that's when we started working on something called visual locomotion. And here the idea is basically expanding on the last point that I mentioned is there's like a hierarchical algorithm. At the top level, there is like a visual kind of perception module that basically takes the vision input and kind of creates an embedding, and that kind of is passed on to the low level controller, which runs at a much higher frequency, typically hundreds, 250 hertz in this case. And at the low level, we use something called MPC. By the way, MPC stands for model-predictive controller, which is like an optimal controller method, and we use that to control the motion of the things, right? So this basically can think of like taking the past kind of thing and now adding vision to that, right? One of the other things that we also do is something called contrastive learning. So among so many other things we tried, we basically try to kind of say that okay, this particular frame should be highly correlated with like a nearby feature frame and less kind of correlated with like any random frame, and use some kind of contrastive labs to try and learn a referential learning that then goes into your value kind of. Cool. Continuing on the different domains, so switching gears again. So now I'll kind of cover some kind of projects in the agile robotics where speed and precision matters. So one question one might ask is like, why do you kind of care about agile robotics? Right? I mean, most of the robots kind of can actually work slowly, but the truth is that if you look at some of the videos, they are typically spread 4x, 3x, 4x, and they kind of work very slowly, and it does get kind of hard to work with the robots if they're working super slowly. And it's not going to scale if you want to actually make robots in the real world. So we are kind of investing some energy into agile kind of domains, and we are looking at a few basically projects such as table tennis, catching, and parkour. And the idea is that this is kind of really push the limits of our kind of control algorithms to the point where we can actually start kind of making good kind of guarantees on a controller so that we can actually work at speed. So the first kind of project in this is what we call as I2R or I sync to real. So here the goal of the project was kind of learn to play table tennis rallies with a robot. Now in the state of the art, typically it's very easy to play against a static ball thrower. Like you kind of have a ball thrower and it just kind of keeps doing balls at you and you kind of hit one ball at a time. That kind of problem is already solved. But the problem is that if you take that kind of controller and try to play a human, the human distribution is very different. Like the way the human hits the ball is very different than the way a ball thrower throws the ball, right? So basically it becomes an experiment problem. To be able to kind of develop a model for playing humans, you need already a controller that plays with the humans, then you can kind of use that to model the human ball distribution. But to do that, you need a controller already. So it becomes a experiment problem. So in this case, what we basically do was like an iterative algorithm. We start with like a small human distribution. We put that on the real robot, and in the beginning, it doesn't play that well. In the beginning, it just kind of hits 1 or 2 rallies. But then we take that data and we expand human ball distribution, and we kind of iterate like 3-4 times. And at that point, human ball distribution covers the overall ball distribution and it's able to play long rallies. So in this case, you can see like basically we are able to generalize the new humans pretty quickly. We kind of create on like 4 different humans, and we are able to generalize much better to like 50 men in this case. And I think the longest rally we got here was like 300 and like I forget, like close to 400 hits, almost like 4 minutes of play. It was like a really long rally, and I was really tired. The robot was not tired by the end of the day.
Question.
Yeah.
So here also is it pixels to action?
Oh, okay, great question. So no, in this case, basically, sorry, yes, the answer is yes, it's pixel to action, but it's a 2-stage process, you know. So here, the input to the overall kind of robot is the vision system. We don't have the ground truth ball information, but first there's a perception algorithm that tries to take the ball location, and that now is fed as an input to the controller, and the controller is trained with the ball XYZ array. So if you look at the end to end, it's pixels to actions, But if you just look at the control part, it's taking input from the perception kind of module that the ball is in. But yes, if the perception module errors and there is noise in the perception, if that kind of starts carrying out, our control algorithm doesn't work.
Also, have you are you exploring, taking videos of two humans play?
Yes,
And
yes,
then using that to train your.
yes, indeed. Yeah, we are doing that. That's a great question. So, this again, you can see this pattern that we start with RL and this kind of train us like, this is an RL algorithm that we kind of train. We are also investing kind of learning from humans. There are kind of certain kind of things that need is like we need a mocap, and we have this set up like a mocap, and also there is some kind of delay that comes between like the actual vision system and the mocap system and to align them. There are some kind of technical challenges in kind of making that work as well. So we kind of chose kind of work on this because RL was showing us some promise, so we continued on the RL thing. But that's not to say that the VC kind of route is not possible. So it's totally feasible that you can actually kind of take two humans playing against each other and then kind of have.
Is there like a goal like you had for chess and Go that you want to be like win the world championship of table tennis?
Yes. Yeah. So that is the deep goal. So we are working on that. So this is kind of the cooperative rallies, and we are actually we are working those complements. And the idea is to kind of create an alpha movement for.
Is the hardware limitation of this where it will be like okay, we are at the limit of hardware.
Yeah, great question. That's another question. So we spent like some time investigating the hardware limits. So we looked at some of the play that goes on, and that's how we chose the things. So this base can move at 3 meters per second velocity and up to I think 2 meters per second square acceleration, and the arm can swing at certain kind of speed, which is in the realm of human play. Of course, if you kind of put like the word number 1 out here, maybe the hardware starts showing up. But if we reach that point, and that's the only reason we cannot beat the word player, then I think we'll still be happy with that, But by and large, for any I would say good universal player or like even like the beginner kind of professional player, the hardware limitations are there. And we also need a lot of space. So you don't see it here, but it's actually 4 meters by 2 meters. There's 4 meters wide and 2 meters deep to give enough space for it to play. And that actually makes the vision problem quite challenging because one thing you don't realize is how large the space is. This camera angle is so big, but since the space is large, the field of view which kind of covers the ball is so small. So we actually have to develop like in-house vision algorithms to actually track the ball at high speed. And this algorithm is running at 100 hertz. So the vision algorithm runs at roughly 125 hertz. So when things are moving and the ball moves at like anywhere from 4 meters per second to 8 meters per second. So we need our algorithm to be really fast. So some of the challenges in these kind of projects are like any kind of engineering system kind of go really fast and be able to control at that kind of precision because small changes in angle will kind of have the ball. Yeah.
So are you introducing like more complex types of shots or slice chopper like top?
Yes, exactly. So indeed we are. Now the question is like how do we introduce, right? So we are kind of hoping that by actually having it practice on its own can kind of get it right. So one way is to do what Bharadwaj just said that you actually have to do display. They show different methods and we learn from them. You can have a thing called like a bag of skills, and then you can have like a complex bag of skills. But I personally think that might not be scalable. So the best way is to actually have it find the patterns by itself by just playing like this. Just play like this, and it itself should find the patterns and should be all learnable. So it should just be kind of able to play, and then figure out. Sure, maybe with some coaching there. So, but that's very good. Sorry, should I repeat the questions? Are the questions audible for the folks? All right. Another kind of quick thing I want to mention is we call something called goal set. So in this we did something which we thought might be useful is learn directly on the real robot. Here the idea is to actually basically have a bootstrap policy in the beginning, and we implement that on the robot, and then we do something called mindset delivery. That says, okay, the goal is to kind of hit a particular target. When the red target is where we want to hit, and but if say we do a mistake and hit somewhere else, we do mindset delivery and say, okay, that should be the target for that action, and we feed that into like a buffer and keep learning. Now the advantage of this kind of method is that we can learn directly on the robot. The previous method did something called iterative simulation. So you have to have a sim, but in many cases, simulation is not even there, right? We want to simulate a clock, we're going to simulate like a fruit or cucumber. It's so hard to simulate it, right? So we say, but in most cases, it's easy to just kind of have a robot do it, right? So we said, okay, let's kind of have a bootstrap policy and then learn on the go. And this was like basically something that showed that this kind of self-improvement flywheel can actually work. But the only kind of key thing is that initial policy, which gives you some success, because otherwise you'll be just kind of trying to hit the ball and missing it all the time. And that bootstrap policy can come from initial pair cloning, or it can come from like some simple algorithm. But once you start planning those, you can do this answer really and then the flywheel kind of.
This is probably a good way to learn all these complex choices.
Yes, exactly, right. So yeah, in fact, we are going to do that right now. Send it there.
Have you tried playing the robot and the robot?
Yes, indeed. You're making me say all my secret progress. Yeah, so that's one of the questions for that. Other kind of quality, I want to mention is something called catching. So here is basically other kind of project, but it has slightly different challenges than ping pong. And some of the challenges here are basically the occlusion. What happens is when you catch the ball, you get occluded as the ball comes to the screen. So almost you're kind of go blind. If you folks play cricket here, you know that you probably might not be able to see the ball when you're catching, right? So towards the end, you kind of go blind because the arm itself is kind of occluding that. So we invested in this kind of project and we kind of investigated two separate approaches for this. One is like a traditional method called Space-Embodied Programming or S2P. It's basically like an MPC kind of algorithm, but it has a better performance for non-linear cost functions. And we also investigated like a traditional algorithm called BGS or black box linear sensing. And in this paper, we basically compared the two. And the key takeaway was black box of the iron algorithm works much better when you are in distribution of balls, like hand throws, right? Won't work if you only are trained on like 1-4 throws, but you cannot go and toss the ball by hand. Even a small change will make it like an auto distribution. But if you stay in distribution, you will high asymmetric performance. But if you kind of go out of distribution, then STP does better. So that's kind of a key takeaway. Cool. The last one is that the identity kind of thing is what we call as barcode. So I think here kind of basically the idea was to kind of have a robotic dog do like an optical course like dogs do, you know, but do it fast. So there's like an A-frame, there's like a jump, there's like a weaving of the poles. So I don't know if you see on TV there's kind of dog games where the dogs do particular thing. We're trying to do the same thing with robot dog game. And we basically have our own kind of hardware inbuilt hardware here that kind of design things. And here we had two approaches that we showed in the paper. This was just recently released, and in the slides there's a link to the paper and the blog post. And basically here we did something that by the mentioning that we have few skill specific policy, walking policy, slow policy, jumping policy, and then we have like a high level policy that kind of has a navigation and high level kind of semantics built into the controller that kind of shows. Then we also explored other controller language and transformer, and what we did was we took all the data from that policy and we actually trained an end-to-end kind of transformer that just kind of gets the robot position and basically kind of outputs the action. And that also kind of showed us pretty good results. So so in this case, like you can see that how you can go potentially from you can follow two of these things. You can have specialized policies and be like a high level on top. And you can also take the data and kind of make it like one fat policy, but then that generalizes and finds the cross correlations between each of those sort of lower level policies. And this is how kind of algorithm things. So we basically are able to kind of complete the optimal course pretty successfully. Sometimes the A-frame is challenging, but we kind of are able to do it pretty well. And actually, if you see it in live motion, it is pretty fast. And just kind of compare, we also kind of compare it against like an actual dog. Of course, not as good as an actual dog, but that's our ambition to kind of make it as an actual dog. So this is like this is a few months back release, and please check out the paper. Not the post blog. Cool. Quickly switching gears here. I want to kind of mention some of the other projects that are going on in this area, which are connecting language and robotics. somewhere around 2 years back, we started realizing like a lot of progress in languages, like large language models, GPT, which became like the basis of chat GPT and all. So we were like, okay, how do we actually lean more into that, and how do we kind of use that to improve the thing? So that then we should be able to just talk to the robot. Just like I'm talking to you, I should be able to kind of talk to the robot and say, hey robot, can you kind of help me with this? And the robot should be able to follow that. So the first kind of projects that we did is what we call as language to plan. Basically, here when I say plan, it's like a high-level task. For example, if I say, get me a drink, the plan will be that, oh, go to the fridge, open the fridge, get a water bottle, bring it back. It doesn't tell me actually the robot actions, but it doesn't tell me how to move the joints, it doesn't tell me how to move the gripper, but it's about like high-level plan. And this it is quite challenging in some cases, but turns out that lens are really good at it. So basically, what we did was start looking at like all these sort of language models like GPT-3, Lambda, PaLM, Flag, and what we found out that okay, if you ask the large language model or LLM a question that hey, can you get me a thing? Turns out that LLMs are quite good at giving a rough plan. Like it will do what I just said like about the thing, but the problem was sometimes it will give you steps which were not feasible in the real world. For example, if I ask it to get a drink, it will just basic knowledge on like Wikipedia or whatever, and it will kind of break down steps. But it's possible in the real world there is no fridge, and maybe the water bottle is right here. So maybe it needs to kind of understand that. So then the question became, how do we take this and ground it to make sure that actually we correlate it with what's actually feasible in the real world? And that was the idea of what we call a SACAN. Here, basically, what we did was on one hand, we take the language model output. The language model gives some options. Like when I say get me a drink, it will give me some options. The language model just gives an option. Step one, go to the fridge, or step one can be just kind of go to the kitchen. Step one, so there are multiple options. And then you have something called value functions. And value functions come from your algorithms that I mentioned before. And the value function basically says what is the feasibility of each of the actions that the language model has proposed. And then we multiply those two to actually kind of say that what are the actions that the language model proposed are actually feasible in the world that we are in right now. And that's how it is able to do a bunch of this stuff. And this was like a pretty successful kind of paper which we call as SACAN. And like a demo of this is like, you say, okay, I stream my thing. The language model says I can help with the mess, I can help you with that, I can vacuum the field. It's a bunch of options, right? They're all options. But now we kind of say, we map it that the value function, and we say that, okay, maybe I see a sponge because there's a vision model and that has a higher value for a sponge, and then it says, bring a sponge. Maybe that's the best I can do, and then kind of iterate on it. So that's how we kind of ground the program in reality using value function. Of course, the key point here is that you have to have that value functions or affordances. So for everything that language model gives an option at the first step, you should have some way of saying that it is feasible or not feasible, and that is a key kind of ingredient of this. The next step we said, okay, second is great, but the problem is in some sense it's open loop in the sense that once it forms a plan, it tries to kind of stick with that plan, and then we said, okay, how about we now kind of form this Socratic model kind of things? That okay, why can't we have more than one model that kind of talk to each other, like, and then kind of one critiques the other model. So you can potentially have a human, a robot, and a scene detector, and something called a success detector, and each of them has their own kind of language model strengths, and they can all basically talk to each other and figure out like what to do. You know, for example, if you see in this kind of thing, the human can say, "Can you give me a soda?" And the language model says, "Yeah, I can find a Coke." And I'm actually going to find a Coke, right? And it's actually tries to get the Coke. The language model suggests pick up the Coke. It's time to get that, but now there's a human disturbance in there, and then the Coke is gone, right? And this basically kind of simulates some dynamic environment. And now there's another model that says it's a different one, and here says action was not successful. And this is like a model trained separately. And now there's like a other robot model that says, well, there's no Coke, but there's an orange soda, is that okay? And the human says, no, bring me a lime soda. Then the robot says, find 11 lime soda, it kind of goes to the kitchen, finds another lime soda, and so on. So basically, the point is that you can basically take the previous idea, add more kind of these language models or large language models who are kind of this thing, and it's like they are all discussing amongst themselves and coming with the right.
So do you
Yeah.
kind of embed the context also in the prompt you give to the language model, or how do you
Do we embed the context?
see context? I saw that you are trying to get this.
I believe so. I'm not 100% sure. So typically in all of these, like the context length is kind of fixed, right? So it starts off with like an initial prompt, and then that prompt has kind of a particular length, and then you kind of keep adding whatever is kind of output till the max length is reached. So I believe the context is fed to the statement. I mean, either part of the input directly or part of the receipt. So this all is fed definitely. If you're asking that is fed to the. Yes.
You have different objects. So, I mean, how much force to apply? Is it pre-trained or is it like depending on the force?
Yeah, it's pre-trained. So that's a great question. We don't have any tactile sensing at this moment, so we can't like really adjust it very minutely. That being said, some of these robots do have this thing called like a indicator force kind of thing. So basically, it is part of the training. I don't remember if this particular model uses that or not, but that is available as a sensor, as like a force sensor to kind of see how much force they're applying. But most of these models don't do that. We just kind of train it, and then success it comes from that. There's a separate line of work that is going on in the top kind of robotic dynamics, and they are kind of built from the top. Cool. Maybe I just quickly mention this. But basically, like we started pushing on the further limit. We said, okay, can we ask LLMs to write code? If LLMs can do instructions, if LLMs can kind of talk to themselves, if LLMs should kind of write code, you know. And this was something we call as code to policies. And here, basically, we did show that you can train these large language models to just output code. So the code can actually contain loops, the code can contain kind of branches like if and whatnot. It's actually producing the code based on some low-level primitives to actually kind of control the robot, and this was like a pleasant surprise for us that actually is able to do pretty well on other tasks. So the good thing is that now this is already robot agnostic because the primitives are robot agnostic, right? So you kind of have this small primitives, the code control is pretty similar. So this was like a pretty interesting project that we did. And some of the example tasks like analyze the blocks in the square. Put the apple and so cool. Now basically other thing that we did was something called PARM, which is like an embedded language model. So far what we saw was taking a large language model and outputting it in like its text form, and then somehow adding the robot component later, either by rounding it into value functions or having them talk to each other, doing some other facilitator. But we said, okay, can we actually now feed the robot data as part of the large language model training itself? So that way, the same model is training on both robot manipulation data, vision person answering, your normal task kind of text prediction task. You know? And that was this project from Kwame. And here, basically, all the input model is like text, vision, robot data, all go to the kind of embedding and go to the same transformer network, and it's like a large like 540 billion parameters. 562 billion parameters, and this showed us like really good success in some of the tasks that we not have seen before. So, apologies, I'm going at a little slightly this space. How much time do I have? 10 more minutes. Okay. Cool. The next thing I want to mention is like language to action. So, as you might have noticed so far, all the things that I said were like language in, but the output was a plan, like something at a higher level. That didn't tell me how to actually kind of control the robot, right? So naturally the question became like, how do we do that, right? So the first kind of project in this is what we call as language table. So here, like Corey, my colleague is basically doing like a real-time interaction with the robot, where you're kind of giving instructions to the robot and it's able to do that. And here, basically, the method was very similar to previous methods.
That's correct.
So as you can see, you can kind of do this like real-time instruction and can form like a really long relevant task by using that short of the task. and each of the short-run tasks were basically trained by the imitation learning, where we collected a bunch of language condition data similar to how we connected for the BCD paper, and this kind of was trained on like roughly 800,000 episodes, which is quite a large kind of data set. So the key here was like large data sets, language conditioning, imitation learning, and basically the right model transformers with a good data set.
To sort of bring it back.
Yeah.
If you look at, say, sports commentary as being another modality to help data evidence.
Yes, that's a great question. Yes. So, but the question is like, how good is the data, right? So, in this case, the data is like very accurate because we got the data labeled by people who know this, right? The sports commentary is very specific. Like a coach is sitting there and giving you commentary about what the person is doing and how to kind of do that, and then we actually kind of collect that data. Then definitely that's good.
You could have a coach for the robot in that.
Right. So, but the some challenges are like it's easy to collect data with a human. For example, like a human can be playing with a paddle, and then the coach can be kind of filling that. But it's hard to kind of have the robot play what the coach asking to do. But then it becomes like a chicken egg problem. Right? The robot is already doing what the thing, then you already have a good policy. So then it kind of becomes like independent control space, and then you need to solve the IT problem to be able to get the right angles. But it's a feasible thing, right? Cool. Moving on. So after language table, we said, okay, can you scale it even further? And that was the genesis of what we call RT1 or robotics transformer 1. And here basically we went back to our transformers, which are kind of showing a lot of kind of promise in the language models and all. We said, okay, why don't we just kind of train one transformer similar to what Kami did, but instead of outputting like a high level plan, we actually output low level kind of controllers, and that was basically the key idea. And here we kind of collected a large set of 330,000 episodes, and we covered like roughly 700 tasks. So this is like a multi-task kind of transformer model. You give it like a bunch of tasks and pass them through like the same kind of embedding and output that. On all these tasks, the input is vision and the output is the end effector control. Oh, what happened? Okay. Yeah. So here one of the key kind of parts of the solution were like a good image tokenization. Basically, you need to find the right tokenization to feed in, and a good action tokenization, and then the token compression. Because you don't compress the tokens, you need a very large model, and then you don't have enough data to kind of fit it, then you underfit it. And this kind of leads to some very nice control. I mean, the breadth of tasks that this kind of control can do is really impressive compared to some of the other methods. So you can basically pick up things, put the things inside the ball, different shapes, different kind of objects and all that, right? And especially when we kind of introduce noise like different distractors, backgrounds, unseen tasks, RT will handle really well compared to some of the other tasks in the message. Cool. Maybe I'll skip the language reward part because I kind of covered some of the other stuff. So, but very quickly, I'm just going to show this video. Here, the idea was that we actually use language to infer reward. So, this is something kind of related to what we were saying before is that here the idea is to use language to infer the reward and then train a reinforcement learning policy to be able to follow those rewards, right? Because typically RL is hard for two things, right? One is that reward is hard, right? You cannot kind of specify all the conditions under which, like, how to specify the reward. But if you specify a wrong reward, the algorithm will exploit, right? So you want to be able to kind of specify the right rewards for the behavior, but it's a big iterative process. Whereas it's easy for human to say, oh, don't give the leg too much, maybe you can put one leg like this, and the key is that how you take that and translate it into good rewards. And that was this project, and then here you can see that we trained a robot kind of do moonwalking in this particular case. And in C, we are successful. In real, we are kind of implementing that. But we did, of course, make sure that in real, it does kind of show some signs of life. It's not all in same. We always try to kind of make sure that it also kind of works in real. So we implemented the same language to rewards in the real world, and we definitely saw some signs of life. There is definitely more gap here than the other methods because we are here kind of doing the dual pattern of vision followed by RF, but definitely there is promise in this. Cool, cool. So basically to summarize, I introduced you to the robotics and Google Deepmind. I gave like a very quick drive-by overview of a few sample projects. Hopefully, you are kind of got a good understanding of the kind of work that we do, the kind of projects we are interested, the kind of method that we are exploring, you know. And then there are links for you to kind of dig deeper. So let's say like where are we heading now, right? So I show you like what's kind of going on roughly now. So where heading now is to basically cross-embodied foundation model. So we are kind of take this and now kind of work on like really robot agnostic, really kind of environment agnostic models that kind of come as like you can think of it like the GPT of robotics. That way you as a lab can take that model and just fine tune it on your use case or just prompt it. Better when you prompt it, you cannot do the answers. You don't have to kind of have the translation. We continue to invest in language between and robotics that gives us like really good wins in terms of our performance. We are also actually interested in human robot interactions and video conditioning, which means that you can just show the robot what to do. Like say even you know like a model and you want to kind of make it work as a discussing this with just unknown. And the human just shows what to do. I can just kind of say, hey, take it out and then open it, and that's what we call as video conditioning, like a few short demonstration, and can the robot do it? So it doesn't need like sequence of iteration, right? Dexterity is another angle we're looking at it. There's a setup called Aloha, it's a proprietary setup that we're kind of using in. It's based out of Stanford, and there's also agility, which cool. We definitely want to hear from you. So there are plenty of opportunities for like faculty to get involved. We have something called like research scholar program. We support kind of early kind of career faculty. There's also visiting research programs quite popular. So we basically get faculty from different universities kind of come and spend 3 months or 3 to 12 months when they're on sabbatical. Some faculty spend like 20% of their time. If they're local, they spend 60% of their time in the office. So like a bunch of kind of possibilities for faculty visiting researchers. And then we have some other kind of programs like award for Indian program and Google Cloud credits for researchers. So definitely look at this kind of link and the links therein, and there's definitely a lot of opportunities for faculty to get involved. There are also kind of opportunities for students. We offer PhD fellowships, like we will kind of fund students supporting their PhDs. There's also research and internships. So we welcome students. We kind of taking a lot of students kind of for internships. There's also kind of mentorship programs that we offer where like a Googler will be an advisor for the person. And if you have any kind of questions, definitely you know contact us at robotics@google.com. Also, you can write to me and refer to the right person. My email is Sanketi, my first initial and last name at google.com. So definitely you can kind of email me, and I'll love to kind of help out in any way we can. And we have the robotics Q&A expert panel. We have like a bunch of folks who are there to kind of help you, kind of guide you and talk to you if needed. Cool. So with that, I'd just like to thank you. And sorry I went like boom, 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 but hopefully it was useful and I will take class. Yes.
Okay, how do you manage about like storing a big model and fast processing and all the vision with like 1 point?
Yeah.
For the large language model.
Yeah. Yeah, that's a great question. So how do we make fast inference with a large language? That's the neat part we don't, you know. So basically right now our large language models are roughly at 2 Hz, 3 Hz. So we have large infrastructure that hosts the models and basically tries to kind of get us as quickly as possible round trip with the things. But if we do like the round trip latency of sending data and getting the things over, it's anywhere from 2 to 3 Hz. So we are looking at making it faster. But if you want to make it faster, we are looking at something called like system 1, system 2 architecture, where system 1 architecture kind of runs at a low frequency, and then there's another controller that runs more locally at a higher frequency, and then we have the right API between the two. But at least as of now, we don't have a way of running a big large language models at a higher frequency. We have kind of make do with like some sort of hierarchical approach with that. Yes.
So all the robots you showed were standalone. So are you working on multiple robots that are communicating with each other and then coming up with a project solution?
Yes, that's a great question. Yes, we are. So I didn't show it in this, but we have like one submission under review that's kind of that where two robots of distinct kind of capability talk to each other and then figure out like, okay, I can't do this, you can do this and stuff like that. You can think of like the inner monologue project I showed as roughly in that category, but we also have other kind of things where we have like a table working robot and we have like a manipulation robot and they go together clear the robot. So one table can only do things and one table can only wipe things and they get together kind of do that. There the key ingredient was basically like infrastructure. The policies were mainly kind of doing the thing. So the key first was infrastructure to be able to kind of have a center this talk to each other and then figure out what the state of the world is.
Then do some projects on kind of autonomous driving using the.
Yeah, so we have some collaboration with Waymo, which is part of Alphabet. So we don't have any kind of direct project right now under that, partly because Waymo is doing that. So we don't have any big research project right now, but we did have collaboration with Waymo in the past on autonomous driving.
So are there a promising direction in autonomous driving or you are trying some different kind of?
So honestly, I don't know what Waymo is doing right now, but when we kind of work with them, we tried basically something like this level NPCs kind of stuff and all that. I do feel that RL has promise in self-drivers also, but there the challenge is safety. I mean, RL is kind of fragile and RL is needs a lot of exploration. The question is like, how do you safely explore? So to me, like the best solution there likely is going to be something we first learn from humans and then adapt it a bit with RL. So to be honest, like I don't know what they're doing right now.
In one of your slides, you were showing something called as safety constraints.
Uh-huh.
So can you explore what kind of safety constraints you added on that?
Correct. So in that case, basically you can kind of think of like some cost functions that penalize you when you go very close to an obstacle, right? Or you basically are going to like a dangerous maneuver, right? Or you can have some sort of constraints on how quickly your leg can move or how quickly you can maybe kick, things like that. So you can input all that in a cost kind of function and use that as a reward in your SSC kind of stuff. You can also use similar kind of formulation in MPC. So RL can do molecular control. You can kind of have optical kind of definitions, and you can say your kind of reward function that you're optimizing on the go with MPC is something that's touching that possible. So it's basically about dependence possible.
And one of your things were like taking inputs from the LLMs directly, and then according to that, the actions you will do will be according to the input from the LLMs.
Yes.
Right. So are you validating the inputs also from LLMs? It may be like there's a person going, you are paying the model to take up a water and there is a person in between.
Yes.
So LLM can give an input like get that person out and then take the water, right?
Yeah.
So it may follow the instructions. So is there any strategy to just validate the instructions first and then do it, or it will do like?
That's a great question. So yes, we do kind of two things there. One is that we
can you please repeat the question?
Allowed list of instructions. So let's say we have 1,000 instructions that are allowed. So it's not like a free form output anymore, but you can have only a set of responses allowed, and the LLM has to choose between the response. It's still a very wide range because you can basically put any object with any verb. So it's only there's like 1,000 structures in there, but you can vary the object and verb, right? So that way you can remove any unsafe activity and all that. And secondly, we also have this thing called some affordances, right? So basically, the affordance tells whether something is feasible or not feasible. So that way, if the LLM is asking you to do something, but that's not feasible, then you avoid that. But the value should be so low for that action that ultimately will say, sorry, I can't do that action, I choose some other action. But yes, I don't mean to say that it's completely solved, but the best thing to is to make it basically have an allow this of kind of sentences only kind of have LLM up to that.
But is it generalizing on this solution, right? It will be too specific to a particular task, right? It cannot be generalized, right?
I mean, it depends. Like, so if you kind of have enough verbs and actions, like you let's say move, and the object is of move, you can kind of say move A to B, and the A to B can be anything. So if A changes and like it's a bottle, not kind of have like a chair, right? You can test reliability, whether the algorithm is generalized or not depends on the algorithm, right? But such a framework does allow you to test for generality. Yeah. So it might be limiting by kind of having like this set of responses, but if you actually look at it, it does allow a lot of actions.
It's like saying robot cannot play for example, cricket and build the support.
Yeah, oh yeah. So if you kind of doing that, then it's like then you basically need to increase your domain, but still you can do the same thing. You still try to make sure that you kind of remove completely unsafe kind of instructions, and also use basically a way to kind of ground it. And there are like three ways you can ground it, whether it's through rewards or through kind of actions or plans. So it's not a problem, but those are methods that are trying to lean towards to actually ground it.
There are two questions online. I don't know if you can see Zoom.
No, I can't.
Can you read them out?
Yeah.
Couple of questions. Maybe you can unmute them.
Yeah, I had one question. I don't know whether I missed the part about are these robots autonomous in the sense all the
One,
You are on Zoom, right?
No,
no, he's not.
no, that's a long game.
Voice is quite low actually.
Can you just read out the question?
Okay. Preetham, can you please type?
Or we can say tough luck. While you
Okay.
Pritam, the voice is quite less. You can type the question actually in the chat.
Okay.
Yeah. So yes, we are hiring. The hiring definitely has slowed down a bit compared to what was pre-COVID. But it's not zero, right? So definitely people move in, move out. When anyone moves in, there's different. Also, there's some shuffling going on. So the short answer is yes, but it's less than other.
So who do they reach out to?
So there's both ways. There are experts that can apply online, and they also kind of go and kind of have campus interviews. So I don't know now whether they are kind of conducting a lot of campus interviews or not, but definitely anyone's kind of free to apply online, and or if you reach out to me, I have to refer you internally also, and that's how the pool is created. Definitely, I would encourage students to get involved in some of the internship and those kind of things, because that's the great platform to get to know if that's a good fit for you, vice versa, and then that pool is also like a great tool from which we hire, because we kind of already know those people who is there. But there are always kind of new hires.
There are a few questions from the audience.
Yes,
So the first question is, what framework is used for these robots? And is the robot operating system used? And what is the simulation environment?
Okay, good. So the robot operating system, we don't use in most of the robots that I showed. Many of them are kind of in-house stacks that we have. That is, you can think of it similar to ROS, but they're in-house, right? So they are not. I mean, some of them are open source. There is this thing called generalist. I think we also have this thing called some of them are open source, some of them are open source. The short answer is that it's in-house. Some of the newer robots we are actually on ROS 2. So it's not like everything is on in-house thing. So we are moving to ROS 2 in some of the robots. In terms of like simulation, we use like a few things. So we use PixBlitz and Joko. We use Unity in the past a bit, but this is mostly Joko and PixBlitz and Brax. So Brax is like TPU kind of friendly simulation algorithm based on JAX, so which people might have heard of. So those are three kind of simulation algorithms which we use these days. Yeah. And was there one more part of the question?
Yeah. So is the inference done locally or on cloud?
Yeah, great question. So for the ping pong robots, we need to kind of run very quickly. The inference is done locally, and by locally, what I mean is that it's connected to a CPU. It's connected like a PC, which is kind of right there and it's connected by network, and it's done there. In some of the robot dock, it's locally, as in like it's actually on the computer that's sitting on the robot itself, right? For some of the manipulation things that I said, like the robot kind of manipulation was moving, there the inference is done on the cloud, because there's like large model, like I was asking, there's a large model, and the other model is on the cloud and it's kind of down to the cloud. So there's a clear kind of frequency trade-off there versus like accuracy.
So does the ML require special network connectivity and OS scheduling?
Sorry, ML requires.
Does the ML require special network connectivity and OS scheduling?
OS scheduling?
Yeah.
No, we don't have any specific OS scheduling. We don't even use real-time OS in any of this. We just use Linux. So we live with the non-real-time thing. So, so in that sense, we just kind of have a stack that has the right threads and all that. Of course, the higher the frequency of the operation, the higher the sensitivity to like the non-real-time OS of that. So the ping pong robots which run at lower than 50 hertz definitely have some of these things. But other than that, we just use like normal threads and processes and like normal C++ kind of coding to make sure that it runs. And what other things? Like some network kind of thing, right?
Yeah.
Yeah. So yeah, definitely we try to kind of keep on network bandwidth as high as kind of possible. Because both for like local inference, when it's talking to a computer and the network, if you want to run at like 250 hertz at the lower level and 100 hertz at the lower level, you want to kind of have like very well fleshed out kind of overall system kind of architecture. So, but other than that, we don't like really try to engineer that. What we instead do is we model those uncertainties in our simulation. So we run simulation, it's closer to some of the other like latency, distribution, and noise sensor.
Okay, so in the interest of time, let's thank Pannag.
Thank you, sir. Thank you for an informative talk. We have arranged for refreshments at the coffee. Please help yourself.